All right, so today we're going to start chapter 5, which I must say is a very intensive chapter because what we have to do here is we have to go through logarithmic functions and exponential functions and go through and learn more about their formal definitions. We also are going to apply integrals and derivatives to both of them. So by the time we're done here, we'll have learned an awful lot of new techniques that will help us understand how to take derivatives and integrals. And it turns out that some of these techniques apply to functions that don't actually include either exponentials or logarithms. So there's a lot going on here in this chapter. So we'll start by introducing the formal definition of logarithms. So, and of course, and this actually comes from the fundamental theorem of calculus because it's defined in terms of an integral. Now, if we recall from the fundamental theorem of calculus, the whole idea of it is that an integral itself is nothing but the area under a curve. So we're going to define the logarithm in the same way. So if you recall the definition that we've been using, f of x is just some function. Here it is assumed to be continuous over some closed interval a to b. Capital F is the antiderivative or integral. And so if you integrate over the interval from a to some x, then what this indicates is that f prime of x, the antiderivative, is equal to this function over the interval from a to b. This is the statement of the first part of the fundamental theorem of calculus. And so what it implies is that for the function natural log of x, where the domain, as you recall, is everything from 0 up to infinity, not including the 0, because the log at 0 is undefined. And so based on this definition, the natural log is equal to the integral from 1 to x, whatever x is, we go from 1 to x, and we integrate the function 1 over t dt. So here's the diagram. So whatever x is, here's the curve, 1 over t. By the way, you notice that they're using t and x. The reason for doing that is to avoid confusing them with each other. So x is some variable, and t is this curve here. This is t plotted against y. And so x tells me how far to integrate. I'm going from 1 to x. Okay. So anyway, the area of the log, the natural log of x, whatever x happens to be, is equal to that shaded region under the curve between 1 and x. And just a quick reminder, this is what the graph looks like of log of x. And you can see that it doesn't quite reach 0. This is an asymptote. And it increases at a decreasing rate. It crosses the axis at 1. Okay. And x is 1. In other words, the log, no matter what the base is, the log of 1 is 0 because e to the 0 power, whatever b happens to be, is equal to 1. And then it just continues to increase at a progressively decreasing rate. So you can see why the domain is everything from 0 up to infinity without including the 0. The range, on the other hand, is all real numbers. As you can see, the function does decrease very dramatically. It becomes negative and it goes down to negative infinity. And on the upside, it does approach positive infinity. By the way, an interesting result here is that if our x is negative, and remember, when the log can be negative, the area can come from the same graph as long as it's understood that this becomes negative. Okay, so for all x's less than 1, the area is defined to be negative. There's this whole area down here is negative. And so therefore, what we're really looking at is the negative of what we're seeing on the left-hand side. It's simply the negative of that same area. All right, anyway, with all that theory out of the way, we start by noting that the derivative, and again, as long as we're in the domain of x, the derivative of log x is simply 1 over x. Okay. Now, if you integrate depending on what your u is, the integral of 1 over u du is the log of absolute value of u plus c. Okay. That absolute value has to be there because of the possibility of the value being plus or minus, as we saw here. Okay. Now, here's some basic properties. You probably remember these, but as long as a and b are strictly positive and r is just some rational number, the log of 1 is 0. The log of a product is the sum of the logs. The log of a ratio is the difference of the logs. And the log of a to the r power is simply r times the log of a. Okay. And the reason for that last one is because let's say that a r is just 2, just to keep it simple. Uh, all right. So in other words, just to illustrate an example of this, if r is 2, then you're looking at the log of a squared, which is the log of a times a. And based on this property, that means it's the same thing as log a plus log a, which in turn is simply equal to 2 log a. Okay, so that's why this last property holds. This last property is essentially an extension of this property. Okay. A few other details. The domain of the log, as we've just seen, is 0 up to infinity without actually including the 0. The range is all the real numbers. Over its range, the function is continuous. And remember, we mentioned this idea of monotonically increasing, which simply means that as x increases, y always increases. In other words, there's never going to come a point where the curve dips down or something like that. So we say that it's not just increasing, it's monotonically increasing. You'll see why that's so important later on in this chapter. Uh, Well, I might as well. I can tell you now what's coming. The fact that a function is monotonically increasing, or monotonically decreasing for that matter, means that we are guaranteed that it has an inverse. Okay, so that's what's coming up later on. We're going to be looking at inverses in a later part of this chapter and how to find them. And we do want to note that this is what we need to guarantee the existence of an inverse, the fact that it's monotonically increasing. Now, the concept of one-to-one is kind of interesting. You can have a function which is not one-to-one. In fact, why don't we just take a detour here, although we'll discuss this again later on in the chapter. What does it mean to be one-to-one? It basically means this. Now, let's say here's x, here's some set x, and here's some set y. And we have here the domain is simply 1, 2, and 3. And over here we have 1, 2, and 3. X will be a function as long as each x is associated with one of the y's. So for example, you could have something like this. And so x equals 1 is associated with y equals 1. So in other words, we could rewrite this as a set of ordered pairs, 1, 1, 2, 1, 3, 3. So this is a function because each x is associated with a single y, but it's not one-to-one. Okay, what does that require? By the way, let's make a note here. This is not one-to-one. But here's one that is. So here's the idea here. Each x is associated with a single y, but in turn, each y is associated with a single x. Okay, in other words, that's not happening here. If you notice, y equals 1 is associated with both x equals 1 and 2. And so while this one on the left is still a function, it is not one-to-one. The one on the right is one-to-one. Because again, each x is associated with a unique y, but y is also associated with a unique x. Okay, so that's the difference between the two. They're both functions, but only the one on the right is one-to-one. And so the log function is also one-to-one, which, like I said, well, you'll see. Anyway, we'll see more about this later on. And then it is also concave down. The second derivative is negative. Um, you can see, because if you come back here and revisit this definition, if the derivative of log x is 1 over x, that implies that the second derivative, which we write like this, be minus x, minus 1 times x to the minus 2. And that's going to be negative. No matter what, no matter what's happening. Okay, so the first derivative of the log of x is 1 over x. The second derivative is obtained by reapplying the power rule to that 1 over x. And so you'll get, so I did something. There we go. Yeah, so you can see the second derivative is guaranteed to be negative. And so that implies that the function is concave down throughout the entire function. Okay. All right. Anyway, now we're ready to start tackling derivatives. So what happens here is that while we know already that dy dx log x is 1 over x, what about more complicated cases? What if we have instead a function of x? So the chain rule for logarithmic functions is stated right here. So instead we have log of g of x, and so that gives us g prime of x over g of x. So this is a special case of the chain rule for logarithmic functions. So that being the case, if we're taking this derivative, what we can do is we can identify g of x is what's in parentheses 5x cubed minus 2, g prime of x by the power rule, is 15x squared, and then we just substitute, and we end up with 15x squared over 5x cubed minus 2. Now, sometimes we can, simplify this. If not, just leave it like that. It's fine the way it is. Okay, so that isn't too difficult. I mean, unless the function itself is a mess, involves sines and cosines, and it could, by the way. It's possible to take a log of a trigonometric function. Now, what about this one? So we have to be careful with the notation. This is the same thing as all right. So sometimes the notation can be a little in math, you have to be a little careful with it. This means that you're taking the log of whatever is being squared here. And if you square 3x, you'll of course end up with 9x squared. So what you actually have here is the derivative of the log of 9x squared. So be careful with those. Well, once you got to that point, g of x is actually, I don't know why this needs to be here. G of x is 9x squared. Based on the power rule, I guess you could say that n is 9. Sorry, k is 9. Remember, the power rule tells us that n k x to the n minus 1. Okay, so here you would have your k, here's your n. So k, nk x to the n minus 1 would be 2 times 9 times x to the 2 minus 1, which is 18x. Okay, great. And now you just substitute. 18x is divided by 9x squared, which reduces very nicely to 2 over x. Or if you prefer, you can rewrite it as 2x to the minus 1. All right, so far so good. I mean, the log functions often are very straightforward. And it turns out later on, we'll see that we can use logarithmic properties to simplify extremely messy problems and turn them into something much more manageable. For integration, if we simply have 1 over x dx, then we end up, when we integrate that, we end up with log absolute value of x plus c. Now, for integrating more complicated functions like this one, in order to have to turn it, or in order for it to be equal to the log, we need to have both g of x and g prime of x. Okay, in other words, it has to be in this form in order for this final result to be log of absolute value of g plus c. If not, then we will need to try another technique, or possibly we may have to supply a constant. Like this one, for example. So you look and say, well, it looks like kind of a mess, doesn't it? What are we supposed to do with this one? Well, what if, now, by the way, when you see that the highest power of x is 1 lower in the numerator than in the denominator, here the highest power is 2, up here the highest power is 1. That's a hint that maybe you'll be able to use logs with this one. So why don't we give it a shot? Let's see if we define g of x to be x squared plus 4. That implies that g prime of x by the power rule is 2x. Aha, so we don't have 2x, but we can supply it ourselves. Multiply here, multiply by half out here, and then all of a sudden, look what we have. All of this is g prime of x dx. And then here we have g of x. Okay. Or actually, we don't. Let me write it like this. It would probably be easier to just leave it the way it is. Let's put it as g prime of x over g of x dx. Now we're good because we know that this is 1/2 log absolute x squared plus 4 plus c. Okay, so this is the log of absolute g of x. And then we need the half because we needed to supply that in order to make this work. So this is our final result. Now it's possible, just because we have a square term here and an x up here doesn't guarantee that we can use logs, but at least it's a possibility, something to consider. All right. So anyway, logarithmic properties. Sometimes we can make things a little simpler for ourselves, like this catastrophe. Look how easy it is. Log 9 is the same as log 3 squared minus 3 log 3 squared. Here we have log 3 to the minus 1. So we have 3 terms, all with the same base. So you just end up with log 3 to the minus 1, or you can rewrite that as minus log of 3. Now, how does that help us? Well, I did mention this a couple of minutes ago. Sometimes we can use the properties of logs to take a really horribly complicated problem and turn it into something much more manageable. Okay, so like here's one. Now, this one is not conceptually difficult because you've got this case. So f prime of x, actually, I'm going to run out of space, by the quotient rule is very simple. Well, I shouldn't say simple. It's straightforward. But when you look at that function, you'll say, that could be a very messy process. And maybe there's a quicker way we can do this. And so what I'm about to show you, sometimes it'll speed things up, sometimes it won't. But what you can do instead is try this. we can try something called logarithmic differentiation. And so basically what you're doing is this. You're taking this function, and you know that you can always apply any function or any technique to both sides of an equation without changing anything. So what we're going to do here is take the natural log of both sides of this equation. So without, again, changing any results. But see, here's the advantage of doing this. We can now suddenly apply the properties of logarithms. And so you can see this can be reduced to 2 log x minus 2. And also remember, this is the same thing as x squared plus 1 to the 1/2 power. So the log can be rewritten as 1/2 log x squared plus 1. Now, once that's done, we can calculate the derivatives of the numerator and the denominator using the rules that we just went over. So for example, let's say you're looking at 2 log x minus 2. So if you think of this as g of x, g prime of x would simply be 1. Okay, so remember from way back here, chain rule tells us, yeah, the derivative of log of g of x is g prime of x over x. In fact, I'm going to copy that just to make sure we can see it. Let's sneak it on here somewhere. Okay, so for this first term, the numerator, we're going to end up with 2. Don't forget the 2. G prime of x is 1. And then we have x minus 2 is our g of x. Oh, sorry. We have 2 over x minus 2 for the numerator. What about the denominator? That's a little bit messier. Let's see if I can sneak it in here somewhere. As far as the denominator is concerned, our g of x would be x squared plus 1. And our g prime of x would be 2x. So therefore, we end up with a half of 2x over x squared plus 1. Okay, so they've both been plugged in here. Now, here's the interesting part. This is the trickiest part of the whole thing. You recall we went over something called implicit differentiation at one point. When you take the derivative of this log of y, here it is. What you end up with is, because y is a function of x, and the log of x has a derivative of 1 over x, that means that the derivative of log y is 1 over y dy dx. Or here, you can write a little more compactly, I guess, as dy dx over y. That is the trick to the whole thing, okay? You're using implicit differentiation to differentiate that log y. It ends up being 1 over y dy dx. Okay, so anyway, that means on the left-hand side of this equation, this is what we have. So remember, though, what we're ultimately solving for is dy dx. So let's bring this all together, and you can see what I've done here is I've rewritten this. Oh, by the way, it looks like, let me just copy this real fast. I consolidated these constants I should have mentioned that. So in other words, uh, um, this becomes 2 over x minus 2, and this becomes x over x squared. Okay. Now, because, ratios is the same thing, as you recall. Actually, suppose you had a ratio A over B over C over D. It's equivalent to saying A over B times D over C. So that means this is equivalent to 2 over x minus 2 times the inverse of this denominator, x squared plus 1 over x. I personally find that's easier to deal with multiplication than division like that. So that's what we have here. Now, then we're going to multiply both sides by this y. So you've got dy dx equals y times 2 over x minus 2 times x squared plus 1 over x. But remember, this is supposed to be a derivative in terms of x. So what we have to do now is substitute our original definition of y into this equation. Okay, it has to be all in terms of x. So when we do that, this is our final result right here. Now, any way you look at it, this is a messy result, but depending on how you look at it, I mean, you could have just as easily gone ahead and done the quotient rule. But when your function gets really, really messy, the messier it gets, the more likely this is to be a quicker and easier way to come up with your derivative. So in other words, it's up to you to decide which approach to use. Although I think in the assignments, it may specifically ask you to use logarithmic differentiation. So, but keep in mind, it's just a shortcut, or it's supposed to be a shortcut. For some applications, it might be more time than it's worth to do it this way. But there's bound to be times when you're happy to have this available to you, because that original function, if it was the more, let's just say that the messier this function is, the more likely it is that logarithmic differentiation will be the way to go. Okay, that it'll become more helpful when this gets very messy. Okay. Wow. So you see that what I mean, this is a lot more than just taking the derivative of a log. You're really getting a lot of other helpful techniques that will speed things up in a lot of cases. So the absolute value, or sorry, the derivative of log of absolute g of x is g prime of x over g of x. So now you might say, well, how does this help me? Well, oh, look at this one. The derivative of log of absolute value of cosine x. So you remember somewhere along the way, we had a chart where we said that the derivative of sine x is cosine x, and the derivative of cosine is negative sine. So here, g is what's inside the parentheses, the absolute value signs, and g prime of x would therefore be, as you can see from here, negative sine x. And so now we just plug everything in. Remember, here's our definition. Sneak this over here. And you can see all you're doing is making the direct substitution. Now, if you feel like it, remember, you could actually do one more thing here. Remember, we defined the tangent as the sine of the cosine. So you could actually go ahead and take this one step further and rewrite it as negative tan x. But I would say that that's optional, unless there's a really good reason for it. But it's good to know that this is true. All right, and like if one of your assignments, maybe they would prefer one or the other. Trig integrals, okay. So now, trigs show up in all kinds of applications. We have to be able to take integrals of trig functions as well as taking derivatives. So what sometimes can happen is if you go to the book where they have that chart with all of the trig integrals listed, or all the integrals are at the back somewhere, there's a huge table that has all of them listed. And if you go there, you'll see that it's going to tell you that the integral of tan x dx is negative log cosine x plus c. It probably has it listed like this to be more general. But remember, u is just some function of x. If it's just x, then you can replace the u with x. So it's tangent x is equal to this. So now we can show why. Because the tangent, as we know, is the sine over the cosine. So we can rewrite this in the following way. So basically what we're doing here is reversing the problem example we just did. We know that the derivative of the cosine is negative sine. So that means that what we actually have here is once we supply the negative, assuming that g of x is cosine x, g prime of x would be negative sine of x. So you've actually just got negative g prime of x over g of x, which means you have negative log g of x plus c, and this is your final result. Okay, so that's why this is the integral of tangent of x. Okay, it's just a straight ahead application of log integration. All right, by the way, I brought them all here together in one place. I find it very frustrating when you have to search around for formulas like this. I wrote it in terms of x, but you could use it for u as well. For example, if you had something like sine 3x or something like that, the formula hasn't changed. It's just that now it's u instead of x. That's all. Okay, so there they are, in case you need them. Also, here's some trig identities that can come in handy. These are based on the Pythagorean theorem, by the way. And you find that sometimes it helps having these at your fingertips so you know how to make complicated situations much more simple. Like this one. Oh my God, what a disaster this one looks like. We're going to integrate from 0 to pi over 4, square root of 1 plus tan squared of x dx. So as soon as you see that square, you'll say to yourself, is it possible that I could use one of these identities to help me simplify it? Well, yeah. Those two, the sum 1 plus tan squared of x can be replaced with secant squared of x. Now, since we're taking the square root, we're taking the square root of the secant squared of x, which means what we have here is just the secant of x times dx. Now, if you look at the table, there it is. So, quick reminder up there. So you've actually got log absolute value of secant x plus tan x evaluated from 0 to pi over 4. Okay, so you have to first evaluate that function at pi over 4, do the same thing for 0. And from the fundamental theorem of calculus, what you're actually doing here is the integral is evaluated at x equals 4 minus the integral evaluated at 0. All right, well, now you have to go to your calculator and look them up. And so you'll find that, for example, the secant of pi over 4 is radical 2. The tangent of pi over 4 is 1. The secant of 0 is 1. And the tangent of 0 is 0. So these can be simplified to the log absolute radical 2 plus 1 minus log 1. This is just 0. You don't need the absolute values here anymore because clearly radical 2 plus 1 is greater than 0. So ultimately, you end up with this result. But the clever part that got us started was this, recognizing that this can be simplified due to the trig identities. Sometimes, by the way, these three are called the Pythagorean identities because they're derived from the Pythagorean theorem. Okay. All right. So otherwise, if you didn't recognize that, you might have been stuck for a long time. Inverse functions. Now, we definitely discussed this during our reviews in the beginning of the course, but let's just quickly remind ourselves how this works. How do you find an inverse? And like I said, if a function f is 1-to-1, then it is guaranteed to have an inverse. So we're going to assume that in these problems, okay? Sometimes you might be asked to show if a function has an inverse or not, but let's assume that it does, and then we'll go ahead with the following techniques. So by the way, how do you prove that two functions are inverses of each other? You have to use composite functions. So remember, this is f inverse. So the composite function f inverse of x, which by the way is the same thing. I prefer this notation because you can see clearly what you're doing. Both of these, f inverse of f of f inverse must give us back to x. Okay, so because what the functions are essentially offsetting each other or undoing each other, kind of like x squared and radical x are inverses of each other. So that means that if I square the square root of x, I'll get x. If I take the square root of x squared, I'll get x. That's how I know that they're inverses. And here's two. Oh, speak of the devil, there they are. So you can plug them in and you can see that it works. Here's a couple more. These are inverses of each other. Sometimes it's more obvious than others. And then we can prove it. Now there's a formal definition in the book somewhere which basically says the following: if two functions are inverses of each other, and A being a point on f of x, then BA is a point on g of x. Okay, so in other words, for any AB on f of x, BA is guaranteed to exist on g of x if they're inverses of each other. So like for here, for example, the point 1,4 and then we have point 1,4 has to be on this function somewhere. Okay. That's all that it means. Okay. And then in other words, that's true for the entire domain of both functions. All right. Anyway, how do we find it? Now that's the fun part. How do we find it? In other words, it's not always so obvious what the inverses are. So here's what we're doing. Let's take this as a simple example. And so what you're doing is you start by reversing the x's and y's. Okay, so here we have y equals 1 over x plus 2. This is going to become x equals 1 over y plus 2. Okay, just like on this point, I mean, you can see AB, I'm just reversing the x's and the y's. So I reverse the x's and y's, and now I have to solve for y. Let's see what we get. So I cross multiply both sides by x plus 2. Now I'm going to distribute this y over these two. So I'll get yx looks like something got left out. Oh no, this should have said um wait a minute, what did I do? That's right, that's right. After we reverse, I just want to make sure because I can see something got left out. It should say x equals 1 over. No. I don't know what happened here. I have to fix this part. It should say x equals y 1 over y plus 2. Yeah, something went wrong. I'll make a note to myself to fix this part. Okay, so what's supposed to happen is that we write this as x equals 1 over y plus 2. All right, let's copy that one more time. Y equals 1 over x plus 2. Okay, that's the function that we want to invert. Okay. So that's what we did here. Now we solve for y. So that means that x times y plus 2 equals 1. That means that xy plus 2x equals 1. Xy equals 1 minus 2x. Y equals 1 minus 2x over x. Okay, that's a lot more like it. And of course, if you want, you could rewrite this as 1 over x minus 2. And then you can confirm this. Again, assuming that f of x, the original function, is here. No, here. So let's write that 1 over x plus 2. F inverse of x, just proved, is 1 over x minus 2. So now how do you demonstrate this? Well, we'll start with this one. F inverse of f of x equals x. Okay. So when you can, this would equal, you take this function and you replace all the x's with f of x's. So in the denominator, we have to be careful here. We have 1 over f of x, which is itself 1 over x plus 2. But now keep in mind that 1 over 1 over is the same thing as 1 times x plus 2 over 1. So that means this term, this expression can be rewritten as x plus 2 minus 2, which is x. Okay, great. Now we have to work this backwards. So here's the two functions. And so what we need to do now is f of f inverse of x means you take this function, replace all the x's with f inverse of x. And then, of course, now luckily these two twos cancel each other out. 1 over 1 over x is the same thing as x. Okay, so that means we did it correctly. All right, good. Oh, by the way, I came up with this interesting application here. Imagine yourself looking at not numbers, but people and social security numbers. Mr. 1 has a social security number 111111111. Okay, now only he can have this number. Number 2 has that social security number. Okay, so in other words, you can't have each person has one social security number, and each social security number belongs to one person. Okay, so that makes this a one-to-one relationship. Now compare that with birthdays. Each person has a single birthday, but many birthdays can have the same people associated with them. So that would be a function, but it's not one-to-one. Okay, it can't be because there's only 300, well, or, there's a limited number of days. If you only look at the day of the year, it's 365. Even if you look at all time, you're going to have multiple birthdays every day. So that would be a function, but not one-to-one. Okay, now, by the way, there's a graphical test you can use to visually see if a function is one-to-one, and it's called the horizontal line test. So let's say we're looking at y equals x squared and y equals x cubed. So the way the horizontal line test works is that if a horizontal line crosses the graph more than once, the function is not one-to-one. So here you can see this one, we say it fails the horizontal line test because you can see the line does cross twice. You just straighten that out just a little. It's supposed to be a straight. Same thing here, and it doesn't matter where you draw it. And so that implies that this is not, but we can show it algebraically as well. Over here, this one passes the horizontal line test. And it is therefore one-to-one. So that's all you need. Just visually, you can see it. A horizontal line across crosses the y equals x squared, the parabola twice. And that means that it fails the test and it cannot be one-to-one, which also means that it doesn't have an inverse. The one on the right, y equals x cubed, does pass the test. It therefore does have an inverse because it is one-to-one. But you can see algebraically why that has to be true. If I pick x equals 2, y equals, but if I pick x equals -2, I also get y equals 4. And so therefore y equals 4 is associated with two different x's, and that means that it's not one-to-one. Okay, whereas over here, x equals 2 is associated with 8, x equals -2 is associated with -8. And so no matter what x you pick, you're going to get a single y and vice versa. So this one is one-to-one. All right. Now, what this is all building up to is the idea that we can actually take the derivative of an inverse function in a very interesting way. We can do it directly using the rules that we know, but there's a way that might provide us with a shortcut. But this assumes that f of x and g of x are inverses of each other. Okay, if not, then none of this works. Okay, so this is the rule, assuming that these are inverses. The derivative of g prime of x, can be found as 1 over f prime of g of x. Now, of course, this is a composite function, which means you're taking the derivative of f of x and replacing all the x's with g of x. All right, so let's look at a quick example of this. All right, so here is x plus 2 over x. Now, let's find the inverse using the technique that we just learned. First, we reverse the x's and y's. Now, when you're doing this, instead of writing it as g of x, you'll want to write it as y equals x plus 2 over 2, x rather. And then you can reverse these x's, both become y's, and this y becomes an x. And then you have to solve for the y. Okay, so algebraically, we multiply both sides by y. We subtract the y from both sides, factor out the y, and this is our final result. Okay. Now, we're not going to spend the time now to prove that they're inverses, but you can do that if you want to. So the original g of x is this x plus 2 over x, and f of x is its inverse, which is 2 over x minus 1. So what we're going to do is find the derivative of g of x, not using the quotient rule that we usually use. Instead, we're going to try this technique, and we'll see what we get. Okay, when we're done, though, we're going to compare it to what we would have gotten by using the quotient rule. So what this is telling us is this. F of x, by the way, we're going to rewrite this like this. Okay, that should be a little simpler. So we need to know the derivative of f of x to make this function, to solve for this function. So therefore, that would be negative by the power rule. Since we started out with 2 times x minus 1 to the minus 1, the derivative will be negative 2x minus 1 to the minus 2, because so here our k is 2, n is -1, So n k x to the n minus 1 will be -1 times 2 x to the -1 minus 1. Oh, whoops, sorry. What did I do? It's x minus 1. Oh, actually, you know what this is? This is the general power rule. The reason why this works here, I just realized we're actually using the general power rule or the chain rule because in the parentheses we have a function of x, but we got a break here because you see what's happening here is that you have if we start out with so this would be our g of x, but g prime of x is actually just 1. So we should theoretically, this is f prime of g of x. The g prime of x that's missing is 1. Okay, so we can still just write it like this. Okay, so in other words, this is it is technically the chain rule here, but because g of x has a derivative of 1, we can just simply write it as -2 times x minus 1 to the minus 2. All right, so remember we started out, this is our original function, this is its derivative. We now have f prime of x. F prime of g of x means that you are replacing all the x's in this derivative with g of x. And that in turn is x plus 2 over x. All right, so let's consolidate the terms inside the parentheses. Okay, here it is again. So I'm going to rewrite this one as x over x. So we're going to have, let's do this on the aside here. Okay. And then, of course, we still are multiplying that by -2, and we're raising that to the -2 power. Now, raising something to the minus power is the same thing as 1 over that raised to the positive power. So, in other words, this is the same thing as having -2 over 2 over x to the positive 2 power. And then when I square 2 over x in the denominator, I get 4 over x squared. Now, once again, we have one of these ratio situations. So actually, I've got no room here at all. Let me fix this. So notice when you divide by a ratio, you're multiplying, it's the same as multiplying by its inverse. So you'll end up with -2x squared over 4, which then can simply simplify to -x squared over 2. So what if we just solve for? We solve for f prime of g of x. But if you go back to the original definition, this is what we're actually solving. So we have, let's make a note here. This is f prime g of x. So there's one more step. We have to plug it into this equation over here. That means the final result is 1 over that. Okay. So in other words, you can see here that, again, f prime of g of x we discovered to be therefore what we're looking for is 1 over that. And that, again, here we go with these ratios. And that's our answer. So basically, the original function g of x was this. So we're saying that by using this technique, we've been able to demonstrate that the derivative of x plus 2 over x is this. Now, what if we had just gone ahead and said, you know what, let's just use the quotient rule. In a case like this, it actually might have been quicker. Okay, let's just try that. Why not? Okay, so if, in other words, we started out with g of x is x plus 2 over 2. This can be thought of as a ratio. Let's call these h of x and j of x. Okay, so h of x is x plus 2. H prime of x is 1. J of x is 2. J prime of x is 0. So there'll be a lot of simplifications here. Let me just make sure I didn't copy something wrong here. I did. I knew it. Something, I copied it wrong. I knew something wasn't right. Oh, Jesus. Let me fix that. This was an X. That's why it didn't turn out right. All right, so let's fix that. J of X is X. After all that work, I just copied it wrong. So J of X is X, and then that derivative is just 1. All right, let's try that again. So you've got G prime of X will be X1 minus X plus 2, 1. There we go. Okay, so in other words, we proved that it, wait, you got negative x squared over 2. Oh, right, because the final answer, God, I was looking at the wrong thing. Minus 2 over x squared is our final result. And that's what we got here. Okay. All right, so anyway, so in a case like this, you might have been better off just doing the quotient rule directly, but it's good to know that you have another option available to you. All right, so that is part A. So what's coming up in part B? Well, part B, we're going to focus more of our attention on e to the x, exponential functions, and obviously integrals and derivatives. And then we'll be looking at some other new techniques. So we'll stop it right here, and then in the next session, we'll be doing 5B. Okay, now, by the way, when we're done, I've also written a set of problems. It's on Blackboard, as Brightspace as we speak, for chapter 5. And because it's such a long and complicated chapter, it's a fairly long problem set, but I'm sure you could use the practice. So once you go look for it, and when we're done with all of this, we'll go through those problems. So I'll see you next time.